Right now, sitting in a drawer of data at NASA's Jet Propulsion Laboratory, there is a 6-year-old open question that nobody could answer with any real confidence, a question left behind by one of the most famous spacecraft in history. In 2012, a machine called Voyager 1 crossed the edge of our entire solar system and sent back a reading so strange that scientists genuinely couldn't tell if it was a real discovery or a fluke caused by broken equipment. For 6 years, that question just sat there, unresolved, because there was only one data point in the entire universe to check it against. Then, in 2018, its twin spacecraft reached that same boundary in a completely different location, and what it found finally closed the case. This is the story of how Voyager 2 solved a mystery that Voyager 1 had no way of solving on its own. I'm your host, and this is Verge. If you're new here, this is exactly the kind of story we come here for. The ones where the answer took years to arrive, and almost nobody outside the research papers ever heard how it actually got resolved. Stay with me, because the mystery itself is stranger than you'd expect. And the way it finally got settled says something important about how fragile even our biggest scientific breakthroughs can be when we only get to check them once. Before we get into it, hit subscribe, because we're just getting started and there's a lot more where this story came from. To understand the mystery, you first need to understand the moment that created it, because this is where everything starts. Voyager 1 and Voyager 2 both launched in 1977, weeks apart, on a mission that was only ever supposed to last a few years. Voyager 1 took the faster route out of the solar system, and in August of 2012, it became the first human-made object in history to cross something called the heliopause, the outer edge of the giant bubble of solar wind that surrounds our entire solar system. Cross that boundary, you've left the region of space controlled by our sun and entered true interstellar space, the region between stars. It was one of the biggest milestones in the history of space exploration, and it came with a serious problem attached to it. Voyager 1's plasma science instrument, the specific piece of hardware built to directly measure the density, temperature, and speed of charged particles around the spacecraft, had stopped working back in 1980, more than 3 decades before it ever reached that boundary. So when the actual crossing happened in 2012, scientists had no direct way to confirm it in the moment. They had to rely on a completely different instrument, the plasma wave instrument, which can only detect plasma density indirectly when something disturbs it enough to make it oscillate, almost like ringing a bell to figure out what it's made of just by its pitch. The problem is, you need an actual disturbance to ring that bell. And out at the edge of the solar system, those disturbances only come from powerful solar eruptions that take over a year to travel that far. It wasn't until October of 2013, more than 13 months after the actual crossing, that a solar outburst finally reached Voyager 1 and gave scientists their first real confirmation of what had happened. And even then, it was an indirect measurement, pieced together rather than directly recorded. That delay alone would have been a strange enough story on its own. But it's not the mystery this video is actually about. The real mystery came from something Voyager 1's magnetometer recorded the moment it crossed. Something that contradicted nearly every model scientists had built to describe this boundary in the first place. For decades, before Voyager 1 got there, one of the most basic predictions about the heliopause was about magnetic fields. Inside our sun's bubble, the magnetic field is shaped by the sun itself. Outside it, in true interstellar space, the magnetic field belongs to the wider galaxy, and it was expected to point in a distinctly different direction. Crossing that boundary should have felt, magnetically speaking, like walking from one room into a completely different one, with the field's direction shifting noticeably the moment the spacecraft passed through. That is not what Voyager 1 found. Its magnetometer recorded almost no change in direction at all. The magnetic field just outside the boundary was pointing in essentially the same direction as the field just inside it, as if the wall separating our solar system from the rest of the galaxy wasn't really a wall at all, at least not magnetically. And here's exactly why that became a genuine unresolved mystery instead of an immediate discovery. Scientists only had one crossing to look at. One specific spacecraft, at one specific location, at one specific moment in time. There was no way to know if that result was a real, fundamental feature of how our solar system connects to interstellar space, or if Voyager 1 had simply crossed at some unusual coincidental spot where the fields happened to line up by chance. Imagine trying to determine the rule for how an entire coastline behaves after visiting exactly one beach exactly once in poor visibility. That's the position researchers were stuck in for the next 6 years. Think about how strange that actually is. One of the most consequential findings about the true edge of our solar system, a discovery that potentially rewrote how the sun's magnetic influence relates to the rest of the galaxy, sat in scientific limbo for the better part of a decade, because there was no second data point to check it against. And building a new spacecraft capable of reaching that same boundary from scratch would take decades. Here's a question worth thinking about for a second, and I'd genuinely like your answer in the comments. Before today, Did you know that one of NASA's most famous discoveries about leaving the solar system was actually treated as unconfirmed by the scientists who found it for 6 full years? I ask because most people assume once something makes headlines as a discovery, scientists already consider it settled fact. This is a perfect example of how often that assumption is wrong. Now here's where the story finally moves, and this is the part almost nobody talks about outside the actual research papers. Voyager 2 had been trailing behind its twin the entire time, taking a longer route out of the solar system by using its own gravity assists to fly past Uranus and Neptune as well, becoming the only spacecraft in history to visit all 4 of the solar system's giant planets. Because of that longer path, Voyager 2 always lagged behind Voyager 1 in total distance traveled, but it carried one enormous advantage its twin didn't have anymore. Its plasma science instrument never broke. It was still working perfectly, decades after launch, all the way out to the edge of the solar system. In November of 2018, Voyager 2 finally reached the heliopause itself, crossing into interstellar space at a completely different location than Voyager 1 had, on essentially the opposite side of the solar system's protective bubble. And because its instruments were intact, there was no year-long wait this time. No need for a distant solar flare to ring the plasma like a bell from far away. Scientists got a direct, real-time reading of the crossing as it actually happened. The plasma density jumped by roughly a factor of 20 within an incredibly narrow stretch of space, confirming cleanly and immediately exactly where the boundary sat and how sharply defined it actually was. For the first time, researchers had a crossing they didn't have to argue about or wait over a year to interpret. And then came the moment that actually solved the 6-year-old mystery. Voyager 2's magnetometer recorded its own reading of the magnetic field on both sides of the boundary, and the result was the same as what Voyager 1 had found years earlier. The magnetic field on the outside lined up with the magnetic field on the inside. No dramatic shift in direction. The exact same surprising model-breaking result recorded by a second independent spacecraft at a different location on the solar system's edge, years apart, under different conditions. That's the moment this stopped being a coincidence and became a confirmed feature of how our solar system actually meets the galaxy around it. One data point can always be an accident. 2 independent data points gathered years apart at different locations by different instruments on different machines, pointing to the exact same surprising conclusion, is evidence. Voyager 2 didn't just add more information to what Voyager 1 had found. It answered the specific question that had been sitting unresolved since 2012. Was this magnetic alignment real, or was it a fluke? The answer, finally, conclusively, was that it's real. Here's why that answer actually matters beyond simply satisfying scientific curiosity, because this connects directly to something that affects every living thing on Earth. The heliosphere, the bubble that Voyager crossed out of, isn't just an interesting boundary floating in space, it's a shield. It blocks the majority of dangerous cosmic radiation, high-energy particles thrown out by exploded stars across the galaxy, from reaching the inner solar system at full strength. If the boundary of that shield behaves less like a clean, separate wall, and more like a connected membrane where the sun's magnetic field and the galaxy's magnetic field are somehow linked, that changes how scientists need to think about the long-term stability and behavior of the exact shield that protects Earth from the harsher parts of the galaxy. This isn't a footnote buried in an academic journal. It's a genuine adjustment to how we understand the mechanism protecting every person who has ever lived on this planet. But solving the magnetic field mystery wasn't the only thing Voyager 2 revealed once it finally got there, and this is where the story takes an even stranger turn, because Voyager 2 didn't just confirm what its twin had found. It also uncovered something Voyager 1 never could have, simply because of where each spacecraft happened to cross. Voyager 1 crossed the heliopause near what scientists call the nose of the heliosphere, the leading edge of our solar system's bubble, facing the direction our sun is moving through the galaxy. Voyager 2 crossed on the flank, off to the side, and the region it passed through behaved differently in a way nobody had predicted. Researchers analyzing the data described that specific area of the boundary as porous. Solar wind particles were detected leaking outward beyond the official edge of the bubble, and high-energy cosmic rays from interstellar space were detected leaking inward before Voyager 2 had technically crossed the boundary at all. The edge of our solar system, at least at this particular location, wasn't a hard line. It was breathing, letting particles pass in both directions simultaneously, in a way that a single crossing from Voyager 1 alone could never have revealed. Voyager 2 also measured something its twin was never able to directly capture at all, the actual temperature of the plasma right at the boundary. The reading came back somewhere between 30,000 and 50,000 degrees Kelvin, dramatically hotter than the calm, cold transition zone models had predicted for decades. The leading explanation researchers have offered is that interstellar material piles up and compresses against the outer edge of our solar system's bubble, heating up in the process the same way snow compresses and warms slightly in front of a plow. It's a real physical squeeze happening at the edge of everything we call home, and it's a detail Voyager 1's broken instruments never had the chance to record at all. So by the time Voyager 2 finished its crossing in 2018, it had done 3 separate things at once. It confirmed, cleanly and in real time, exactly how sharp and sudden the transition into interstellar space actually is. It resolved the 6-year-old mystery about whether the strange lack of magnetic field rotation was a real, repeatable feature of our solar system's edge, or just a fluke from one lucky or unlucky crossing. And it revealed something completely new, a porous, leaky boundary and an unexpectedly hot, compressed layer that Voyager 1's incomplete instruments were never in a position to detect in the first place. It's worth pausing here to understand exactly why scientists take single, unconfirmed results this seriously instead of just accepting the first exciting headline and moving on. Throughout the history of astronomy and space exploration, there are plenty of examples of a single measurement turning out to be an equipment glitch. A strange local anomaly, or coincidence that looked meaningful until a second, independent check either confirmed or quietly disproved it. The entire discipline of science is built around exactly that kind of skepticism, especially when the stakes involve rewriting a decades-old model of how something as fundamental as our solar system's boundary actually behaves. A single crossing, no matter how historic, is still just one sample size. And when you're trying to describe a boundary that stretches across an area of space so vast that scientists still don't have a precise map of its overall shape, one measurement from one specific point is genuinely not enough to confidently generalize from, no matter how carefully that measurement was taken. This is exactly why Ed Stone, the project scientist who guided the Voyager mission for decades, had been clear for years that the entire point of eventually getting a second spacecraft out to that same boundary was to answer a very specific question. Were the things Voyager 1 found actually representative of the whole heliosphere, or were they simply unique to the exact time and place where that one spacecraft happened to cross? That is precisely the question that sat unanswered for 6 years. And it's precisely the question Voyager 2 was finally able to resolve the moment its own instruments confirmed the same magnetic alignment in a completely different location. Now, let's bring this into the present, because this story isn't just history. And the 2 spacecraft at the center of it are both still out there right now, in 2026, still working, still transmitting, and still running out of time. As of this year, Voyager 1 sits somewhere around 15.5 billion miles from Earth. And it's on track to become the first human-made object ever to reach a full light day of distance from our planet in the middle of November this year, meaning a radio signal will need a full 24 hours just to travel from Earth to the spacecraft, one way. Voyager 2 currently sits farther back, around 13 billion miles out, with a one-way communication delay of nearly 20 hours, and it isn't expected to reach that same one light day milestone until roughly the year 2035. Both spacecraft are also losing power every single year, generated by radioisotope thermoelectric generators, essentially containers of decaying plutonium that produce heat, which gets converted into electricity, and that output cannot be refueled or repaired from billions of miles away. NASA's engineering teams have spent years carefully deciding which scientific instruments to shut down and in what order, trying to squeeze the maximum possible scientific value out of a power supply that keeps shrinking. Current estimates from the mission team suggest meaningful operations on both spacecraft will likely continue only into the early 2030s before power finally drops below the minimum threshold needed to keep any instrument running at all. Which means the specific method that finally solved the 6-year mystery we just walked through, having a second working spacecraft available to check the first one's results, isn't something we're going to have the luxury of repeating anytime soon. There is currently no interstellar mission funded or in development that would replace either Voyager once they finally go silent. If a new probe were designed, funded, and launched starting today, using current propulsion technology, it would take decades just to reach the boundary. These 2 aging machines are already sitting inside of right now. For the foreseeable future, Voyager 1 and Voyager 2 remain the only 2 real independent checks humanity has ever had on what the true edge of our solar system actually looks like. And soon, we'll be back down to 0. And solving that one mystery didn't close every open question tied to this boundary either, which is worth knowing before we wrap up. Since 2017, Voyager 1 has been detecting a strange, persistent hum in the plasma surrounding it, a continuous signal that researchers still can't fully agree on the cause of. One explanation is that it's simply thermally excited plasma, vibrating in a way that fits neatly inside existing physics. The other possibility is something called quasi-thermal noise, a different underlying mechanism that would require meaningful revisions to how scientists model the interstellar medium altogether. Distinguishing between those 2 explanations requires more data than either aging spacecraft can realistically provide at this point, and there's no new interstellar mission currently funded that would settle it anytime soon. So, while Voyager 2 closed the book on one long-standing mystery in 2018, It also became part of a much bigger, still unfinished story about exactly how much we still don't understand about the region just beyond our own front door. Here's the piece of this that I think deserves to sit with you the longest. It's tempting to treat a big scientific discovery as finished the moment it makes headlines, especially something as historic as being the first human-made object to leave the solar system. But real confidence in a result like that often depends on getting a second independent look from a different angle, with better instruments, before anyone can really say for certain what was true and what was simply a one-time snapshot from one specific place and time. For 6 years, one of Voyager's most important findings sat in that uncertain space, neither confirmed nor disproven, simply because there was nothing else out there to compare it against. It took a second spacecraft, launched the same year, built by the same engineers, finally reaching the same edge from a different direction, to turn that lingering question into an actual, confirmed answer. Somewhere out past 13 billion miles right now, a machine built with technology from the 1970s, running on less electricity than the light in your refrigerator, already answered a mystery that took the scientific community 6 years to resolve. And it's still out there, still transmitting, still capable of surprising us before its power finally runs out for good. If this kind of story is exactly what you come here for, subscribe and turn on notifications, because we go deeper into stories like this all the time, and you won't want to miss the next one. Let me know in the comments what surprised you more. The fact that one of Voyager's biggest discoveries sat unconfirmed for 6 full years, or the fact that the edge of our solar system might actually be leaking in both directions at once. And if you know someone who'd find it fascinating that it took a second spacecraft, launched the same year as the first, to finally settle a mystery this big, send them this video, because stories about how science actually gets confirmed deserve to reach more people than the algorithm usually allows.